We're starting with this chapter about, we've discussed parametric regression, we started with linear models, we went to some additive models, we discussed non-parametric regression, we discussed smoothing, we discussed various types of smoothers, and we have some ideas about both sides of the table, and we want to understand, like, because we understand that non-parametric regressions do not assume a particular structure. By definition, they can subsume parametric regression models in a sense. Um, and so this is about testing the parametric regression specifications using these non-parametric models. So what exactly does specification mean in the first place? So specification is basically when you encode your assumptions. So you have some assumptions about the process. That is the very basis of learning a function to fit some data, because you think that there is a function and you want to learn it, which is an assumption in the first place. And you make assumptions on top of that, like, okay, this function might be a straight line, and therefore you have your linear model. You assume that this function might be quadratic, therefore you have your, well, quadratic, cubic, etc. All of those are encoded as polynomial models. So in general, that is your model specification, and that's what that means. So encode your assumptions, or what we expect the data generating process to be like, in the form of a model. So one important use of non-parametric regression is testing whether parametric regressions are well specified. Like, are these the right assumptions? Is the true data generating process really a linear model? And that's what we do. So what this says is, if you have your y, your response variable, as a function of your a independent variable and the parameters, plus some uncorrelated noise, how can we tell if the specification is right? So take an example. Suppose it's a linear model. Then you want to compare the fit you obtain by using a linear model specification, and the fit you obtain by using a quadratic model specification, and then compare that, okay, is the linear model fit actually equal to or better than the quadratic model? Like, you want to say in these two, actually let me use my pencil. You want to say that if you fit these two models to the same data, this coefficient should be close to 0. Nearly 0. So that's what you want to see. Or but this is not always the case. Like, there are corner cases that exist, which actually might happen a lot. It's not really a corner case. These might be cases that occur in real life where you have finite number of samples. So this fit might actually give you a smaller error by overfitting on your data than this one. So in that case, can you really use this sort of model to, like, in that case, what do you do? What can you say? And this chapter is about basically highlighting what happens, the corner cases, and how to get past those corner cases to actually use these kind of tests to check if this linear model can fit your data properly, or not fit your data, but if this is the true model, if the model specification is correct, if the parametric model specification is correct. And we use these kind of non-parametric models to check those. Just for the record, this is still a parametric model. It's just not a linear model anymore. The idea is, this is an example of how you can use more complex models, the limiting example of which could be a non-parametric model. Limiting case. So I wrote down a bunch of explanations for this, for when you actually read it and you want to go back and understand what it means. The general idea is, you might know that your model is wrong because you get a poor fit to the data. Your model specification is incorrect. but you don't always know how or which assumption is wrong. So you don't know like where you went wrong, but you know you went wrong. And the idea is you want to be able to tell what is right. Like, of course, you care about going like knowing when you're wrong, but you also care obviously about knowing what is the right answer then. And the idea is under certain assumptions, non-parametric tests can be used to test these parametric model misspecifications. On the note of underspecified models, on the note of misspecification, there's a recent paper and I saw some tweets about this. There were some 39 co-authors from Google who wrote a paper about how models are underspecified and how that affects production deployment and stuff like that, and with some examples of how that goes about. It's like a big collaboration and it got some visibility. There was also some drama around it because Judea Pearl commented saying, under like it took you 39 people and so many experiments to just come up with the answer that, oh, these models are underspecified, because it's so simple. Um, it's a simple conclusion to arrive at. He said that someone in high school could have arrived at this conclusion, and that drove a lot of criticism, saying, okay, anyway, there was drama around that which focused on, okay, underspecified models, neural networks are underspecified, something like that. Look it up. Anyway, here the idea, remember again that once you fit your x to your y, what is remaining is the residual, and what we want is the residual should have no structure, because you have assumed standard noise. So if your model is correct, if your model is correctly specified, then the residual should not have structure. But if the residuals from the second model are significantly smaller, and the significantly is important here, than the residuals from the first, then we need to check. Then there is clearly something going wrong with the first, or the first one is not fitting the data well enough. So that's what this whole comparison is about, and this significantly is what we will go deeper into understanding. Like, what is the significance? How do we test it? Yeah. This can work if you have chosen the right nonlinearity to test. It has the power to detect certain misspecifications if they exist, but not others. So remember that even this model, you're making some assumptions, right? So you need to know that, okay, at least if you're comparing against this, then this has to be the true model. If it's not, then this will also have some errors and so on and so forth. So that's why I said this is still a parametric model. The limiting case of other such models will be a non-parametric model, which does not make such parametric assumptions about the structure of the process, but instead learns about the structure from the data. It has its own problems, as we will see, but that's the general idea, that, okay, don't already assume structure, but if you do already assume structure, then use some sort of test that doesn't assume structure to check if your structural assumptions are correct. And that's what this power to detect certain misspecifications refers to. So, and he gives a nice example. We assume this was linear versus quadratic, but what if it's cubic? What if it's polynomial? So on and so forth. So that's the motivation for non-parametric regression. Like, you can use more complex parametric models, but ultimately, like, the best idea is to use a non-parametric model, because it lets you check for all kinds of systemic errors rather than singling out a particular one. Yeah, Sarmishta just woke up. Okay, we're good. So 3 basic approaches, which he gives in order of increasing specifications, increasing sophistications. What did I mention here? Yeah, so the simple way, before we get into like testing all of these things, in general, people don't, or at least when I say in general, he means most popularly people ignore these issues. They just assume this linear model is the true model. So when you do your regressions and stuff, people typically give you explanations for why the true model might be linear, and then they just work with the linear model, but they don't always test those assumptions and show you that these are reasonable assumptions from the data. I don't know, at least that's what he's saying, that people generally just ignore the issue. They don't really care about, okay, what if this is wrong? But more and more people are caring about it, so this approach is gaining in popularity. So, increasing order of sophistication of checking for all kinds of systemic errors. The first approach is, if the parametric model is right, it should predict as well as or even better than the non-parametric one, and we can check whether the mean squared error of the parametric model is close enough to the mean squared error of the non-parametric model. Footnote. Is it on the next page? Yeah, so why it is the same or better than, is the reason for this is that, remember, the smoother must use up some of the information in the data to figure out the shape of the regression function first, and then actually fit that regression function to the data. The parametric model, on the other hand, the smoother is the non-parametric model, right? The parametric model, on the other hand, takes this basic shape as given. That's our assumption, that we assume the true model is linear, and then within that linear space of functions, we use all of this data's information to tune its parameters. So it's like a informal analysis of why the parametric model should fit as good as or better than the non-parametric model if the model specification is correct. So if the parametric model is right. So that's number one. Number two, if the parametric model is right, then the non-parametric estimated regression curve should be very close to the parametric one. So we can check at every point the parametric prediction minus the non-parametric prediction is approximately zero everywhere. I don't think I want to say anything more about this. Fairly straightforward. And third, if the parametric model is right, then its residuals should be patternless and independent of the features. Because, and I provide an explanation of what he's saying here. I should highlight this. Basically, expected value of y minus the predictions from the parametric model, given your covariates, is equal to this thing, is the true model, right? So the true model and the learned parametric model belong to the same class. So you will ultimately learn these two, learn the true model, and this will be the same. So it will cancel out, and what you're left with is the uncorrelated noise. Uncorrelated means this is equal to well, I've written it down already. Uncorrelated means the conditional expectation is equal to the marginal expectation, which we assumed to be zero. Zero mean uncorrelated noise, right? So we can apply non-parametric smoothing to the parametric residuals. Parametric residuals and see if their expectation is approximately zero everywhere. So that's like writing this down in mathematical form. I don't know what expectation zero everywhere means, because my understanding of expectation is anyway implying everywhere, right? You take all of the samples to calculate that expectation. I don't know. If you have a better understanding, please let me know. Also, I guess I assume this is like to detect structure, to see if there is to calculate it. So the way I was thinking about it is that I can calculate the expectation of the residuals without actually fitting a non-parametric model to it, right? Or do I still need to fit a model to it? Like if I'm at some point, he says that the expectation is basically just the squared residuals, the sample squared residuals. But I guess you need to fit a model and then take the expected value of that fit. I don't know. I'm a little confused about why he says we can apply non-parametric smoothing to the parametric residuals. Like why? Maybe I'm missing something. Okay. We'll stick with the first procedure because it's simpler for us to implement computationally, which is this thing, the mean squared error of parametric minus non-parametric. But it turns out to be easier to develop theory for the other two, and especially for the third, this thing. What he says is, once you have the data, fit a parametric model and get an estimate theta. This is straightforward. You can think of this as linear regression. You get your in-sample mean squared error. Fine. Now fit using the same data, fit your favorite non-parametric regression. Again, we've seen multiple methods: kernel regression, spline curves, other ideas. Getting this estimated curve and the in-sample mean squared error for that, and calculate this mean squared error. Fine. Up to this, it's the point number one. Right now, after this, simulate from this parametric model. So you fit a parametric model. So you fit a parametric model to the data to get fake data. So this goes back to the point of your bootstrap stuff. This goes back to, okay, now, actually I should explain, no, I'll explain what we're doing after I go through this algorithm. So generate fake data from that parametric model, fit the parametric model to the simulated data, getting this estimated theta hat star. So, okay, new parametric model, fit a new non-parametric model, and on this fake data, compare the difference between these two fits, the mean squared error of these two fits. So what I did was compared the mean squared error difference on the original data, then using bootstrapping, I compare multiple differences between mean squared error on the new fake data. Now this fake data is generated from an actual parametric model, right? So in principle, or at least as far as the theory we have read goes, this parametric model should fit equal to or better than the non-parametric model because the true model is parametric, right? That allows us to say that, okay, if we consider the null hypothesis that the true model is correctly specified, and now this is in general, like for this data, then the p-value of this procedure should be very low. Oh, sorry, very high. And I'm not going to get into p-values and hypothesis testing because I assume you can go through Carlos's notes and read about that, or hopefully you have already. But I do provide an explanation here, so if you want to go through that, feel free. I'll read it out anyway. Yeah.
So I had a question about this.
Hmm?
I understood what we are doing till step 6, right? But
Okay.
when we are trying to calculate, when you're trying to calculate the p-value, ideally, if the model is correctly specified, we want many d star to be greater than d hat, right?
Yes.
Yes, but what I didn't understand is why there would ever be a case where d star would be greater than d hat, because d hat is on the actual data. From that actual data, we calculated a parametric model and then we simulated data accordingly, right?
Could you
So
repeat
the
that
mean
part?
square error
Yeah.
on, yeah, just 1 second. Yeah,
No, no, complete your
we
thought.
had some actual data. We can, yeah. So what I'm trying to say is D star since it's based on the simulated data, so D star has two components. It has the mean square error of the theta hat star and mu hat star. Mu hat star we can assume to be constant because it's a non-parametric model really won't be changing a lot, right?
What do you mean
It
by
won't matter
constant?
whether it's from the actual data for this. Why would the mean square error from the non-parametric model change? Even if the data was from the parametric model, if it was the actual data for or the simulated data, it would still be the same, right?
I don't think so. The mean squared error will change based on the data, right? It won't be the same.
Okay, okay, I'll try to simplify my question. I'm just trying to understand how would it be possible that any D star value would be greater than D hat? Why would it ever be the case? So that's what I'm trying to understand.
Okay, so let's take a look at d star and d hat again, right? D hat is mean squared error difference on the original data. Now, note that we don't know what the original model actually is, right?
Yes,
Original
we don't
model
know.
can be well specified or misspecified. So,
Yes.
take two cases. Suppose, let's start with the simpler case. Suppose that the original model is also linear. Okay, I'm going to take
Okay.
specific examples so that this is very concrete. Suppose true model is linear, parametric model is linear, right? Then by definition, this will be lower than this, equal to or lower than. So this value will be really low,
Yes.
right? Correspondingly, this value will also be really low. Now I don't know how to, if I can build a comparison of d star versus d hat, whether it's greater than or less than, but bear with me here. So these two are extremely close. Um, um, if the true model is linear, and
Yes.
the number of times, will this be greater
So
than or less than?
what I was trying to imply here is from the original data, actual data, we calculated a theta hat, which was a parametric model. Now using that parametric model, again we are trying to we simulated some data. So obviously that data, the mean square error generated by by using the same parametric model on the simulated data should be lower, right? So the first component of D star should be smaller than the first component of D hat. Would you agree with that?
Yeah, I will agree with that.
So in that case, what I don't understand is then if the first component is smaller,
Hmm.
then how would D star mean how would you get a considerable number of D stars to be greater than D hat?
How would you get a considerable number of d star to be greater than d hat? I'm formulating my answer to be more technically precise. Um, in a case, so let's work backwards, right? If d star is greater than d hat, what happens? If d star is greater than d hat a lot of times, then this means that the p-value is high, right?
And you have a good fit.
That
Your
means
parametric
your true
models are good
model
fit.
is actually linear.
Yes.
I'm going with the example I set up earlier, but this just means the parametric model is right. Um, which means the error from the non-parametric model will be greater than or equal to the error from the parametric model,
Yes.
right? Which means d hat will be less than d star. Yeah, that makes sense. So if we go backwards, that makes sense. Now I have to come up with a forward explanation. um, the forward explanation is if going back to your question, when would we get a substantial number of d stars to be greater than d hat? When the true model is correctly specified, you can say that this will be a very low number, this will be a higher number, this quantity will be negative, this will be roughly zero, this will be roughly zero
The same
because it
as
will be able to discover the true model.
no, but it will be the same as MSE of mu hat, right? Why would it be different? Why would MSE of mu hat star be different from MSE of mu hat?
I see, now I get your
Like,
question.
that's just random chance, right?
That's just random chance, yeah. And I think he explains this at some point that there is a chance that the reason we're doing this bootstrapping is to get over the possibility. Oh, in the intrinsic noise of the process. He explains this somewhere. Right here. So why do we need this hypothesis test using the p-values? I think because I thought of this question and I came up with this like this curiosity itself. So smaller errors for the smoother suggest that the parametric model is wrong, but since the smoother has a higher capacity, it could easily get smaller errors on a particular sample by chance and or overfitting. So only big differences in error count as evidence. So that's like big differences in error are only going to happen when there is a misspecification in the model. So you're right in the sense that maybe this should be close to and far apart from as opposed to smaller than or greater than, and that would make things more clearer. um, I don't know why he's written greater than, but if he's written it, it should probably be the case that this is necessarily less than d hat if you consider
So, if I can offer an explanation, I'll try. But when you use the originally fitted parametric model to simulate data, you're essentially saying that my view of the world initially was correct, and if it is, and because of that, this is how the data should be, and you that's how you create new data, and you give it to the parametric model and the non-parametric model again. And if it was a well specified model, then this error shouldn't be much because essentially you just have random noise at that point, and so the errors will be small and they shouldn't be significant. But if it is a badly specified model, then obviously there is some a pattern to the residual in the fitted model, right? Sorry, in the parametric model. And so that residual pattern will still be there in the new simulated data because it's still a badly fitted model. But your non-parametric model will fit to that properly, and you'll have larger errors. You'll have larger D stars. Does that make sense? Because
I Yeah, yeah, please continue. Sorry.
no, so because before, when in the original, in the actual data, you would have some data that actually tells you how the world should be, right? Like you have a badly fitted model, and so MSE of theta cap will be larger, which means MSE of theta cap minus MSE of the non-parametric model will not be as great, as big. But when you are giving it data that it thinks is correct, the MSE of theta star cap is about as small as it can get. So it will just be random noise.
Okay, so if I could present a counterpoint for that. Okay,
Mm-hmm.
if assuming that the it's not a linear model, assuming that the true model is supposed to be a quadratic curve, and we are
Mm-hmm.
trying to fit a linear model to it. That
Mm-hmm.
means our means for d hat means MSE of theta hat will be large,
Mm-hmm.
whereas MSE of mu hat will be small because it's a non-parametric model. It doesn't depend on what we define it as.
Yeah.
So d hat will be a large value.
Yeah.
Now, using theta hat, we simulated some data. Now,
Mm-hmm.
theta hat is supposed to be a linear model, and the
Mm-hmm.
simulated data will also be it'll also fit on a linear line, right? Because we are
Right.
simulating from a linear line. That
Right.
means MSE of theta hat star will be small,
Yeah.
and MSE of mu hat star will still be the same as MSE of mu hat.
Right. Oh, this is
So,
annoying. Yeah.
so
Mm-hmm.
in this case, I can still understand why p-value would be smaller in this case. But
Yeah.
what I don't understand is the positive case. And like in the negative case, I can get why you would use a p-value. In the
Mm-hmm.
positive case, I think from what we have discussed right now, I think it's just you try to do it 200 times or 300 times. By
Mm-hmm.
random chance, some of your if your D star and D hat are going to be close, then sometimes you're by random chance because you have that noise, right? We add a noise while simulating data. So just due to that noise, sometimes D star will be greater and sometimes D star will be small. So I think that's just the explanation. I don't know any mathematical proof for it now.
Mm, I don't know. The other ways, like they have explained only method one, right? But method two and three seem easier to understand to me. Mm. But how does this make sense? You're right. It does feel like it'll only be random data, like random data points. Sorry.
Yeah, even in the example which they gave,
Hmm.
even when the model linear model, even when the
Hmm.
true model was supposed to be a linear model, the p value was still only 0.3. Like you would expect if in normal operations, if something is correct, you would expect a large value, right? 0.8 or 0.9.
No,
Like if
not necessarily.
I mean, generally something is right, don't we consider it to have a value larger than 0.5 if you
If
want to prove
I'm
something?
if I'm not wrong, for p-value greater than zero point 0.1 is also considered significant. It depends on your this thing. This is a weird p-value test, though. What would you consider significant here?
I have an idea. I think I can. I'm trying to get my whiteboard onto this photo.
Parth, I think both you and I understood p-values wrong.
Um, I don't know if this will sync with my.
Because a p-value less than 0.05 is probability that the null hypothesis is false. So
Yeah.
you want it to be smaller, right?
Only if the model is not fitting, right? If the true model is not linear. However, I mean, so I understand your point. If in p values, I didn't know this, that in p values even a value of zero point 0.1 can be considered as a positive result for the hypothesis, null
For the
hypothesis.
null hypothesis, yes.
I thought that like most things you would expect something like zero point 0.5 plus or something. I didn't
Mm.
realize that.
Um, so if I can offer some idea, and
Mm.
you can tell me if this is right or wrong. Um, I should probably just shift my laptop screen. Just don't want to lose. But I'm not screen sharing, so how do I? Oh my god. I'm sending. I'm sending a an image on the group.
On the Slack channel or on
Yeah,
the
on the
chat
Slack
here?
channel. Sorry.
Oh.
Okay, so I sent a message on the Slack channel. I think this is the case. So the idea is, when we say well specified, we don't necessarily mean that it is still exactly like the exact specification matches. So in general, real world versus this made up problem in the sense bootstrapping, right? Made up problem will always have equal to or better structure than the real world, right?
Yes, because it's simulated data.
Because simulated data, which means MSE theta hat star, that is the made up world parametric model, will always have a better fit than the MSE theta hat. Is this agreed?
Yes.
Okay, so that is in the picture, the leftmost comparison. The lower theta hat star MSE is less than the upper theta hat MSE. Okay, this holds in general. I should have added a blue also. Never mind. Now go to MSE mu hat, right, and compare that with MSE mu star. I'm not comparing theta hat mu hat right now. I'm just comparing mu hat mu star. So consider a misspecified model. MSE mu hat will fit worse than MSE mu hat star. Do you buy that? So MSE mu hat will be greater than MSE mu hat star because in both cases it is a non-parametric model. But in the first case, there might actually be no structure in the world to be found. So that is as good as a misspecified model.
But doesn't since you don't have to manually define the structure for a non-parametric model, it doesn't really make a difference, right?
Okay, so
You can't say that for sure.
in that case, I'll say greater than equal to.
I mean, in fact, in the textbook, I think just below the algorithm, just below the steps, they actually say that it will reduce. If you look at, I think you highlighted that line as well.
Where is this?
I think in the paragraph on page 192.
Paragraph on page 192 will be converging to the smallest level compatible with the intrinsic noise of the process. Yeah, I agree with that, but I'm saying in the made up problem, like the one below it, bootstrapping, whatever, it will have an equally good fit because that is definitely a structure that is contained within the non-parametric model. So even if the real world has a structure that is really good, it cannot have a better structure than this exact parametric model that we have used to simulate the data,
True, true.
right?
Yes.
So MSE mu hat star will necessarily be less than, maybe I will add equal to, just because I don't want to make too strong an assumption. Less than or equal to MSE mu hat. Do you buy this?
Yep.
If you consider a well specified model, then that is the case of the equal to. That was what I was trying to get at, but I guess we've already discussed that. um, so in both cases, like MSE of mu hat is greater than equal to MSE of mu hat star. So you establish two relation. If this is not clear, ask me. I will go over this again because this is also like clarifying for me. Okay, assuming it is clear. So we've established two things so far: relationship between theta hat star, and relationship between mu hat star in terms of mean squared error. And we have established that in both cases, whether it's a well specified or misspecified model, the upper ones will be greater than or equal to the lower ones. Now let's look at the relationships between the two upper quantities in case of a misspecified model. So if it's a misspecified model, parametric non-parametric regression will discover the structure better than parametric regression, um, which means the black arrow MSE of theta hat is greater than MSE of mu hat. This is agreed.
I'm not sure. I think that actually depends on what non-parametric model you're using. Because in the example which they gave,
Uh-huh.
even when the true model was a linear model and the parametric model was linear as well, uh,
Oh, I'm
the
talking about
D.
misspecified models.
Oh, sorry.
Yeah, the black. That's why I color coded this. So I'm talking about the black stuff. In case of the misspecified model, the MSE of theta hat is greater than MSE of mu hat.
Yep.
Okay. Now, in case of a misspecified model, look at the lower problem, right? The lower problem doesn't care about the specification because you're generating from theta hat star and fitting theta hat star, which means it will necessarily be less than or equal. I should have added equal to. Less than or equal to MSE of mu hat star. This is agreed upon. Black arrow, lower one holds. Okay, I'm going to assume that's a yes.
No, again, I'm sorry. I mean, I was just thinking about that, and I just think that depends on the non-parametric model which you're defining, which you're
Uh,
using.
yeah, so I'm
I
saying add an equal to there.
Yeah. Okay.
Yeah,
Yeah. Okay.
I didn't add. Yeah, I didn't think that through. But if I say less than equal to, you buy the lower black arrow, right?
I didn't understand why it would be, but yeah, I think so. I didn't understand why you can say that.
So you're saying you're simulating from that model and fitting the same model. So that's why I'm saying if it's the same class of models you're fitting, then by definition, or he said it here.
Yeah, I
In
said it. Yeah.
Sorry.
Yeah, I understand. I mean, I can understand the logic, but I think that just depends on how much noise you're adding and how that noise varies in that particular simulation.
How that noise. So in regression, you're going to have the same. Okay, let's consider zero mean noise. I think the noise is uncorrelated zero mean and standard variance, right? Homoscedastic noise. He's mentioned this somewhere.
Yeah, yeah, it's almost correct. It's mentioned in the examples.
Right. So in that case, since we are simulating, we control that for every example, right?
Yes.
So in that case, would you agree the lower black arrow holds with an equal to sign?
Okay.
Okay. Now consider the well specified model, which is the blue arrows, right? So upper two quantities with respect to the well specified model. Um, he's already given us this that the MSE of theta hat, the parametric fit, will be better than or equal to the non-parametric fit. So that error will be lower because it uses all the information just to tune the parameters, whereas in the non-parametric model you use some information about your data to actually find the class of true models and then fit the parameters for that model. This was in the
Yes.
footnote that we explored on page 193. Remember that the smoother must use some information to figure out the shape of the regression.
Yeah, I agree with this.
Okay, so the blue arrow upper one holds. The blue arrow lower one, if it's a well specified model, wait, the blue arrow lower one well specified model should be the opposite. Yikes.
Yeah, this is this seems weird. Like, how can you say that? Yeah, despite using theta hat to simulate data, how will the
Yeah,
mean square
yeah.
error
The
increase?
blue arrow lower one should be the reverse. Yeah, which is okay. Which yeah. Okay. Blue arrow lower one is reverse. Okay, you buy that, right?
Yeah, yeah.
Okay. Now, given all of this, let me write it on my blackboard. Now, given all of this, let's calculate what could happen to the p-values in both cases. I don't know where my duster is. Ah, ठीक है.
Parth, if we assume that, like if we take the standard of p-value being less than equal to 0.05 for the null hypothesis to be true, even if you do 500 tries on this model, you just need like two or maybe three times where the condition is satisfied and it's considered to be significant. Three times, sorry.
Yeah, I understand that. So I guess that just depends on random chance, right? And like when you're adding noise.
Hmm. It's
So
unlikely to depend on random chance because when you add random noise, your parametric model MSE will also reflect that random noise, and assuming like it's a well fitted model and all that, and it should be. But in this case, in theta star, sorry, in theta kappa case. And the MSE of the non-parametric model should also be random noise, so it should be very close to zero.
okay, so I think what they're trying to say is in the case of I think that's what you're trying to say as well, that when they are well specified, D star and D will be very close, D hat.
Mm-hmm.
Yeah.
So So there will be a few instances when D star becomes greater than D hat.
Mm-hmm.
It'll be very rare when D star becomes greater than D hat, and most of the time it'll be, and so that is why we consider only like bigger errors, right? The smoother should get rid, not get rid of, but this is like small errors for the smoother aren't really considered in this case, if that makes sense. When the model is well specified.
But we aren't really. I mean, I didn't see any step where we actually decided what threshold we would use for deciding whether an error is small or large.
Yeah, I know, but in the explanation there, they say smaller errors for the smoother then suggest that the parametric model is wrong. But since smoother has higher capacity, it could easily get smaller errors on a particular sample by chance and or overfitting. So only big differences in error count as evidence.
So I think just rather than just doing it on the actual data once,
Hmm.
the step that we are doing taking by doing bootstrap and then doing a p-value test, I think that is what he means. That will show us whether there is a significant difference. If we just do it
Hmm.
on the actual data, then d hat in some cases d hat might end up being like if I use a different non-parametric model, then my MSE NP of mu hat will change.
Hmm.
So that is too dependent on your non-parametric method, or it's just random chance at that point. But if you're doing 500 tests or something by using Bootstrap, then it becomes significant if the same pattern shows up again and again, I guess.
Hmm. Hmm. I feel like if it is just random noise, that both the parametric model and the non-parametric model can't fit in both cases, then that random noise, assuming that it's been sampled from a similar normal distribution, that should be zero, right? Because assuming you have enough data, central limit theorem should hold, and the MSE, like the differences in both cases of the MSE should be close to zero.
Yeah, I guess. Yeah, I think that happened in the example as well. Like the differences were like 10 raised to minus 7 or something.
Mm.
I guess we can just continue the chapter. Maybe in the example, we'll get some more clarity. I think I understood what the idea is.
So this is D hat, this is D star. Yeah, I'm trying to build a sort of numeric example to consider how the relationships vary with a misspecified model and a well-specified model. Um, what I'm getting is D star will be less than D hat for the well-specified model, which is fair, right? Yeah, in case of misspecified model, no. Yeah, I'm doing something. Yeah, never mind. But this is a good question. Build a sort of I will try to build a better intuition of this by using a concrete example and like using this what we just discussed of the relationships between these MSEs. Um, let's well, since I've written about it, might as well go through it. The question of interest is if the true model is parametric, can the non-parametric model still fit the data better because it has higher capacity slash overfits the sample? This is like the corner case that would ruin our analysis because otherwise we can perform a correct analysis very straightforwardly. But because this non-parametric model might still give us a better fit, even though um, true model is linear in some cases, just because of the sample. That's why we want to do this bootstrapping. So the experiment is sample from this fitted parametric model and compare errors from non-parametric model on these samples with that of fitted parametric model on original data. We've been through all of this, and I'm not going to confuse you further until I build that good example. Um, I guess skip this part. It's a general strategy of bootstrapping. Nice callback. He goes through a nice example in R about how this works. Like he gives us the algorithm and the code to run this algorithm, which is really nice in my opinion. So he simulates a true model, which is non-linear. Then he fits it with a linear model. So the true model is this gray line, which is visibly non-linear. He fits it with a gray line, which is this, with a black line, which is like a linear model. And he says that this is actually a good approximation as it turns out, because the r squared, which is the explained variance, this thing is 86%. So this just based on this, it might seem to you that okay, true model is linear, but remember that this p-value reported is also very very low, which means the null is p-value is very very low, which means the null can be rejected. Oh, then okay, yeah. But remember that all this really means is that you'd have to be crazy to think a flat line fit better than the straight line with a slope. So just rejecting this null, um, I guess that's what he's trying to say. Um, the in sample mean squared error of the fit, and he says something about that, but it's not very important unless you want to go into the semantics of R code. Still, I've provided an explanation of what this means, this 300 and 298, where this comes from and why it's important to us. But again, that's R code and you don't have to go into the details. What he does is to verify that it's not just the case that this higher capacity non-parametric is fitting the data. You want to compare p-values for this. I guess I need to explain the previous section in order to get to this example better. Um, what do I want to say about this? I don't think I want to say anything about this. It's just an example representing what we discussed earlier, except in this case, it shows that the non-parametric model has a smaller MSE, which means the linear model is not the correct model, like the model is not well specified. So he highlights that this is how it occurs in practice. But what we were getting at is the proof for this, like why do we need to consider those p-values? Well, the simple version of it is to say that sometimes, even though sometimes the non-parametric regression fits the noise. It's as simple as that, I guess. Yeah. Sometimes the non-parametric regression fits the noise, which means it can still have a smaller mean squared error than the true model. Right? That's the idea. And in order to avoid that, we want to average out these cases of overfitting because it won't always overfit. I guess that was the discussion we were also having, that overfitting is sample specific. Sometimes it can't overfit because you have to consider that it also has finite samples. In the limit of infinite samples, it would be different. It would always overfit because it has enough data to overfit and enough capacity to fit all of this. But in the case of finite samples, the non-parametric regressions can't always overfit, which means if we do bootstrapping, if we take multiple examples, in most cases at least, it will not overfit. In some cases, it might overfit. So this mean squared error in general will have a higher value than the parametric model if the model is correctly specified. Hopefully that's clear. If that's not, ask me to repeat that. That part at least we can clear out right now. Should I repeat that?
Were you discussing in this case? I'm just clarifying this. Are you discussing this case where non-parametric regression has a smaller MSE?
I'm discussing the case where the non-parametric regression has a smaller MSE, but not with respect to this. In this case, it's the true model is misspecified. I am saying even if the true model is correctly specified, sometimes non-parametric regression fits the noise. If it fits the noise, sometimes then that means it has a smaller mean squared error.
Yeah. Okay. Yeah. Yeah. I
But
understood. Yeah.
that does not necessarily mean true model is incorrect. That does not mean
Yeah. I got. Yeah.
parametric model is incorrect,
Yeah. I got your explanation. Yes.
right? So in order to avoid these corner cases where it fits the noise, you take many different samples, fit many different non-parametric regressions, fit it many times, and on average you say that it won't always overfit. Fair? Okay. So then we can say that,
Also,
yeah.
sorry, just a question. Is the assumption here that the non-parametric model has infinite capacity, or does it have a limited capacity?
So that's what we discussed, right? So if you assume infinite data and then computation is not an issue, then we can fit that model to the noise.
Yeah, not infinite data, like limited data, but infinite capacity. So in that case, essentially, whichever non-parametric model you choose doesn't matter much.
We're saying it has a higher capacity than the parametric model.
Okay, fine.
Right? And then infinite capacity isn't. I mean, both of them imply the same difference in mean squared error.
Do they?
No,
Because if your non-parametric model has lower capacity but infinite data, it doesn't matter. It won't be able to fit to the data.
That is true. Oh, I meant infinite capacity and greater capacity than parametric models.
Okay, yeah.
Both of those things imply the same thing. Yeah, not the data.
Yeah, for this purposes, for this case, yeah. Fair enough.
So yeah, we want to ignore those. Firstly, we won't have infinite data. That is a valid assumption, and it is an assumption made here because otherwise it will change. Secondly, we do assume it has a higher capacity. We know that it has a higher capacity. We assume computation is not an issue, but we assume finite samples. So the while it may sometimes still fit the noise because of this sampling procedure, most of the times it will not. Which is why bootstrapping will work, which is why we actually do that to compare the mean squared errors. Okay. Moving on to, yeah, this part relies on our understanding of our code, so it's not specifically important.
Honestly, building intuition for the third approach that they provided is a lot easier than the first one, even though the first one might have been easier to show, I guess.
So it's just the guiding theme for this is that it's very unlikely that a non-parametric regression would improve so much on the linear model if the linear model were true. This is the statement we're trying to explore when you consider all this hypothesis testing stuff. We want to see if this is just a random chance or an actual thing. That's it. In this case, we know that okay, true model was non-linear. We fit a linear model. We fit a non-parametric model. On average, the non-parametric model has much lower errors. So this distribution here, the p-value is extremely low. And so we can reject this null hypothesis, which was that the parametric model is true or well specified. which means we can't work with a linear model. Here our parametric assumption was linear, and therefore we need to work with a higher order model and then test the null for that and all of that. But that's the idea, to reject the fit for the linear model using this non-parametric regression. He gives another not a counter example, but a second example to prove the opposite also works. Now he says consider the true model being linear. You can simulate, you can do this whole study again. What you will find is the p-value is 0.3, which is a very high p-value. Note that your significance level alpha is usually 0.05. Significance level matlab p-value. Okay, I was going to get into this anyway. Just an overview of p-values, right? In general, what you want to do with hypothesis testing is you pick a null hypothesis, which is to say, this is what I think, this is one way of what the world might be like. You explain your assumption for the null. Now you pick your alternative hypothesis, which is to say, this is what I think the world might also be like, and I want to see which one of these the world is actually like, right? What you need for this is a test statistic T, and you want to see the distribution of values for this test statistic. I mean, I don't need this thing. So under this null hypothesis, I say that, okay, suppose this test distribution is distributed this way, right? A majority of this test statistic falls under this bandwidth, let's say. Okay, this is under my null hypothesis. This is my test statistic values, and this is my probability distribution function. This is a very hand-wavy explanation, right? So under my null hypothesis, if this holds true, that is, if Modi is a good prime minister, then test statistic, which is my GDP growth, will be roughly this way. So let's say 6%. This is actually, I should have flipped this. Well, GDP decline, let's say. Okay, my GDP is declining, my country is dying. If Modi was a good prime minister, GDP decline would be 0.1%. Okay, not a lot. It's declining very slowly, so he's doing a good job of saving the country. Okay, and my alternative hypothesis is Modi is a bad PM, and I observe from the data I have, I see that GDP is declining at a rate of 25%. My country is really going to the dogs. And under the null hypothesis, this 25% is somewhere here. So the probability of this 25%, or the p-value, I think that's what the p-value is referring to, is very, 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 very low. The p-value is like the y at GDP is equal to 25. This is test statistic. Let's not say GDP. This is test statistic. Value that I observed is very, very, very low. So clearly this would be very unlikely under the null hypothesis, which is why I reject this null if the p-value is very low under the null, and I say that, okay, my alternate hypothesis therefore must be true. And that's what significance level alpha means. You set this level alpha under which you want to reject the null. Hopefully this provided an intuitive understanding of how they work. Please also look it up yourself. I don't know if this is the best way to explain it. I just came up with this on the spot and tried to explain it. Typically this alpha you set at 5%, or was it 0.95, because we actually check 1 minus alpha. Yeah, no, 0.05, you check 1 minus alpha, so that's 0.95. Yeah, so yeah, that is hypothesis testing your null, or your alternative. Now you can draw your analogy between this thing. Your hypothesis is that under the null your d hat minus d naught d star is very close to 0, and your alternative is your d hat minus d star, let's say mod, is very greater than 0. So I guess that's what we are testing here. I don't think it matters that, no, they said the number of times d star is greater than d hat, which means this mod is definitely should be d star minus d hat. I don't know, I mean, hopefully you understand that apart from the signs, this is the idea. The signs, I will try to work out an example and confirm what the signs should be in cases of well specified and underspecified model. D star should be necessarily lower than d hat, right, if the model is well specified. I don't know. Anyway, so one of them, this is your null hypothesis, whatever the direction of the signs, plus or minus 0. And like, let's just keep this mod for now because I'm explaining this without this thing. And you want to check that, okay, if under the null the distribution of my test statistic is like this, and I observe a value of d star minus d hat somewhere around here, then clearly this is not the correct hypothesis and I should go with my alternate. Or if my p-value is high and I'm like, okay, this is the p-value I observe, then I can say that, okay, under the null this is perfectly plausible because it has a high probability of occurring. So my null hypothesis is true and my model is correctly specified. Parametric model is correct. Yeah, hopefully that was an introduction to p-values if you didn't have one already. More precise estimate, bootstrap more. That I think we've been over before in bootstrapping also. But this is like he gives us a nice set of examples before jumping into, okay, but in the real world though. This was for one-dimensional. In a fully non-parametric alternative for multivariate regressions, it's going to be time consuming. I thought I wrote about this. I really thought I wrote about this. What? Yeah, it was just what I wrote was remember that the convergence comparison for O of n by p raised to minus 4 by 5, like non-parametric regressions converge very slowly. So and that gets at what he says later about the power of loss of power in the test, because if your non-parametric regression doesn't converge only, you can't really use it to compare, and like your test is not powerful enough to compare that standard error or that mean squared error to the mean squared error of the parametric regression, because parametric regressions do converge fast. So yeah, that's one part of the problem, is loss in power because convergence. This looks more like sigma, I should make it O. And the other part of the problem is your computation. Like with dimensionality, it becomes computationally very expensive to run multiple, and remember that for each bootstrap sample you're running regression, non-parametric regression, so like it's very challenging. Compromises test it against an additive model. We did go through general additive models in the last chapter, so I will not go very deep into this. This is fine. There is another interesting section. I thought I had made notes for this also. I don't know. I think my notes didn't sync. I hope I didn't lose it. Essentially, he's just talking about the things that we have been over. And he says a natural test statistic is the size of the residuals, which is interesting. I haven't really, I didn't really analyze this in detail, but is essentially saying get an estimate of the expected value of the squared errors. So estimate is basically 1 by n average sample mean residual, I think it's called RSS, residual squared samples something, but yeah, I have come across this term before, RSS. And then go through the same procedure again, finding the residuals by fitting the parametric model, smoothing the residuals to get r hat, calculating this size, the concept of size is given here, this, and then simulating to get a distribution for how big those residuals should be under the null hypothesis that the parametric model is right. So new test statistic, just as we defined GDP, we defined d minus d star minus d hat minus d star, whatever this was. So we defined this, we defined GDP. Similarly, another test statistic can be a residual RSS or size of residuals. And then again do the same thing under the null hypothesis that the parametric model is right. How big should they be? How big are they actually? What is the frequency of them being bigger? And then calculate p-values and reject the null or accept the null. An alternative to measuring the size would be to try to predict the residuals. We could compare the MSEs of the model, that the residuals have conditional expectation 0 everywhere, to the MSE of the model that predicts the residuals by smoothing against X and then proceed as before, which is, yeah, difference in MSE for the residual, blah, 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 blah. Fair enough. I'm like I mentioned before, like I'm not completely clear on this part, smoothing against X. But I guess that just requires me to read things again and understand it. So far we have looked at the difference in mean squared errors. The bootstrap principle being invoked is that the sampling distribution under the estimated parametric model should be close to the distribution under the true value. Sometimes some massaging is helps to bring these distributions closer, but that could pin over that in bootstrap stuff. Some modifications to consider. This is a typical thing people do, because I've come across this in causal inference as well. Like you compute the standardized mean squared error, which I mean I don't disagree with it, but like sometimes it's hard to motivate these things. So it's interesting to see them do this. I guess what you're saying is if your noise varies a lot, then you want to reduce this MSE, because that probably varies a lot given your data. Divide an estimate of the noise sigma times the difference in degrees of freedom using the effective degrees of freedom of the non-parametric regression. Oh, I made a side note on degrees of freedom, which is basically your number of observations minus number of parameters. So here, since we're estimating 2 parameters, that is your y is equal to beta naught plus beta 1 x. Your degrees of freedom are number of observations, which he takes as 200 minus 2, 300 minus 2. At least I think so. Yeah, 300. Yeah. Okay. So that's your degrees of freedom idea. So you can imagine the more complicated the model you assume, the less your degrees of freedom. Where was I? Use the log of the ratio in MSEs instead of the MSE difference. Yeah, fair enough. Different metric. Um, Doing a double bootstrap can help you assess whether these are necessary. Okay. Like this seems like a lot of work, but I guess that's the point he's driving home, that it is very popular to make the assumption that okay, we are most likely right, but it is very uncommon to actually test whether you're right or wrong, because it is this much effort for every single time you are saying okay, I assume a linear model. Why use parametric models at all? This is a great question. So far we have seen that parametric models, we can use non-parametric models to test parametric models, but why not just use non-parametric models to fit them? Like you're saying that non-parametric will fit the right things the right way, at least better than parametric models will, without making all of those assumptions. So why can't we just use non-parametric models? And it goes back to these two problems. What the hell? I just stated this. Yeah, these two problems that we discussed. One of them is convergence is slow in multivariate cases, and second, it's still computationally expensive. Um, a third thing he mentions is interpretability. So remember that we discussed this in non-parametric models, that one crucial issue is you can't really say with linear models you can say if x1 changes by this much, y1 will change by beta 1, right? In non-parametric models it was not that trivial. Like you had to multiple, and we mentioned this, you had to visualize multiple curves to actually see how some change in some values might affect a change in y. Like it wasn't straightforward. So interpretability is big in science, especially because the theories are ideas about mechanisms generating the data. um, of course sometimes you actually know the model is linear, but sometimes parameters themselves are meaningful and interesting, and we don't just care about prediction. So interpreting linear models is important. And don't forget that non-parametric methods will have larger variance at the same sample size than correctly specified parametric models, because bias variance trade-off. Um, yeah, I think this is enough. Yeah, that's all I want to say about that section. Now, why do we sometimes want misspecified parametric models? Sometimes processes are simpler than they actually appear. Like sometimes due to natural phenomena, there might be periodic outliers or some random shit that makes a process appear more complex than it actually is. But the what we want to learn about the process might actually be expressed well enough by a linear model. So that's one reason why we want to learn a linear model. In other cases, like there might be, you can break the process into some interesting and uninteresting substructures, of which the interesting substructure is linear. I guess I said the same thing in different ways. um, I guess that's the example he gives here. Again, I'm sorry I lost my notes about this. I guess that was that I saved a different version when they just asked me. Stupid. Um, yeah, I don't think I want to say anything about this example. It's fairly straightforward to read it. It's just like the bias variance trade-off. It says for the non-parametric regression, um, non-parametric is lower bias, linear model is lower variance. So which there is a trade-off between both of those, and this demonstrates in some cases that that trade-off might be in favor of the parametric models as opposed to the non-parametric models. And that brings us to the end of the chapter. This has been very interesting, to see that okay, we can actually quantify assumptions, calculate how far we are off and why we are off and how we are off. He gives some references, but mainly econometrics is has like econometrics will consider this relevant. because of this testing your assumptions basically. Mainly because I feel the field is largely reliant on regression analysis, and in that case, you would want to quantify these assumptions, especially the uncertainty and where you go wrong. And that's about it. That is the chapter. Questions, comments, feedback. And I hope I was recording. Yes, I was recording.
Did you guys hear about how the president is now saying that Moderna and Pfizer are developing vaccines to delay his re election?
Let me stop recording first.